All right, looking at section 7.5, exponential and log functions. So it says for an exponential function, if a, your base, is greater than 0 and a does not equal 1, then the exponential function with base a is f of x equals a to the x. Well, why all the restrictions on the base? What appears to be the problem? So let's experiment. So grab your graphing calculator and let's graph y equals negative 2 to the x. And let's see, where is the problem? So I graph it and I used a special window, Zoom 4. Zoom 4 counts by a tenth, 0.1, 0.2, 0.3, 0.4, 0.5. And as you can see, half my points are above the x-axis, half the points are below, nobody's connected together. In fact, there's major gaps in between here. And just to explain why of all the gaps in my graph is I went to the table, started at negative 2.5, counted by 0.5, which means I'm counting by a half. And you'll notice that all the 0.5s have an error message. Well, that's because 0.5 is 1/2. Negative 2 to the 1/2 power, that's the square root of a negative 2. That's the imaginary value. So our problem then lies, okay, if I can have possible fractional powers and I have even denominators in those fractional powers, a 2, a 4, a 6, a 8, a 10, a 12, those are all even roots, and we cannot take an even root of a negative number. That's why we have all these gaps. This thing is nowhere close to being continuous. So that's our problem with having a negative base. Okay, so we don't want that. I understand that. We got it. What's the problem with 1 as my base? Well, I went to y1, took out the negative 2, put in a 1, and holy cow, I graphed it. I get a horizontal line. My y's never change. Okay, well, that makes sense. That's not an exponential function. That's a constant function. All right, so we don't want that one either. So I get it. We have to have a positive base, but it can't be a 1. All right, I buy into that now. If we do some more experiments with our x's and our 2 to the x, strange things happen when we have negative x's. If I have negative 1 going in from my x, 2 to the negative 1, that's my negative exponential function. All right, that means I got to use my negative exponent rule, which says, okay, the base is in the numerator. Move it down to the denominator with a positive 1 for its base. That's 1/2. Same thing if I put negative 4 in for x. 2 to the negative 4 moves the 2 down to the denominator with a positive 4, which is now 16 in the denominator. 1/16. If I do negative 6, okay, that's 2 to the negative 6. That's 1/2 to the 6. That's 1/64. What can you conclude about the function of f of x equals 2 to the x as x approaches negative? And wait a minute, we saw this before. Yeah, when I have a 1 on the top and my denominator keeps getting bigger and bigger and bigger, we're approaching, and it's going to equal 0. All right, I should say approaching 0, maybe not equal 0. So y is equal to 0. That's my horizontal asymptote. Does this left-hand behavior change if you choose a bigger a or no? Anything that's greater than 1 is going to cause these values on the bottom to keep getting bigger and bigger. What if we have positive exponents? Well, f to the 0, 2 to the 0 is 1. F of 1, 2 to the 1 is 2. F of 3, 2 cubed is 8. Now it appears that my numbers are getting bigger and bigger and bigger. So what can we conclude about f of x equals 2 to the x as x goes to infinity? Our y's are going to go to infinity. All right, let's look at a graph of our exponential function, say 2 to the x. Okay, rule 1, I'm not filling out tables anymore. I'm going to let the calculator do that. I already had it in my calculator as negative 2x. I'm just going to change it back to 2 to the x. I did say that wrong. Negative 2 to the x, not 2 to the x, or 2x. Okay, anywho, here's my graph. My table. So let's build our graph. Now, we said previously we have a horizontal asymptote. Let's plot that first. There's my line. Now at negative 2, I'm at 1/4 or 0.25. When I'm at negative 1, I'm at 1/2 or 0.5. 0, 1 on the y-axis right there. 1, 2, 2, 4, 3, 8. It's just a little bit off the graph. There's my exponential curve. So 1/2 is going to be approaching 0. The other right-hand behavior will be approaching infinity. Now, real quick, I want to point this out. Remember when they asked us, does this matter what base you have? Think if I have base 3, 4, 5, 6, 7, 8, 9, 10, so on and so on and so forth. This point 0, 1, really important, because 0 goes into the exponent for any base. A to the 0 power will always equal 1. So 0, 1 is known as the common point because every exponential function has to contain that point. My domain of my exponential function is all real numbers. My range, 0 to infinity, because we have to stay above the x-axis. This function, reading it from left to right, is constantly increasing, and it's always continuous on its entire domain. And as we said, the x-axis is my horizontal asymptote, which is y equals 0. Now, we have what are known as basic points. Again, here's my common point right there, 0, 1. Everything starts there. Now, you move your x 1 unit to the right. Well, a to the first power is a. You go 1 unit to the left. A to the negative 1 is 1 over a. So these are 3 really good points to start with for any exponential function. But if your base is small enough, like our base of 2, then 2 squared is 4. I was able to fit that point on my graph. If this graph had counted up to 10, then I can fit in 3 comma a cubed. So if you have a small base, you want to check maybe 1 more unit to the right of 1. Check what happens when x is 2. Alrighty. Well, what happens when we have a base somewhere between 0 and 1? What's going to happen here? So let's choose 1/5 to the x. Putting in my negative 1. Oh, wait a minute. We're going to have all negative exponents. Wait a minute. Negative exponents on a fractional base is going to flip it to a 5. 1/5 to the negative 2 power, flip it, 5 squared, 25. 1/5 to the negative third, flip it, 5 cubed, 125. So now, as my x approaches negative infinity, my f of x, my y's, they are getting bigger and bigger and bigger. They're going to infinity as well. Okay, so if now we head towards, well, excuse me, does the left-hand behavior change if you choose? Nope, still stays the same. Doesn't matter what fraction between 0 and 1. But if we go positive powers, non-negative, 1/5 to the 0 is 1. 1/5 to the first is 1/5. 1/5 to the third power is 1 over 25. Now we're going smaller and smaller again. So now again, we're approaching 0. So we still have our horizontal asymptote at y equals 0. So thinking about this graph, let's go build an example of this. It appears that your left and right hand behaviors switch. So f of x equals 1/2 to the x power. Okay, to my calculator I go. Put in 1/2, raise it to the x power. Here's my numbers, negative 3, 8. Or I guess I should put in my horizontal asymptote first. I apologize. And whoops, I think I'm going smaller numbers. Yep, 2 and 1/4, 1.5, 0, 1, negative 1, 2, 2, 4, or negative 2, 4, negative 3, 8. So as you can see, the graph appears that it has flipped over the y-axis. So we're no longer increasing. We're going to have to answer that down here. Domain and range stay the same because all we did was flip over the y-axis. Now we're decreasing and we're still continuous. Our x-axis is still our horizontal asymptote. Y equals 0 as your x keeps getting bigger to infinity. And again, you can always put in that extra point as part of your basics. Now, sometimes you got to put it over on this side as negative 2, comma 1 over a squared. So we can get that point right here.